Homage to the Bridge Builders imagines an adaptation of London Bridge as an entry into the pedestrianised city. London Bridge is a specimen of transport infrastructure, regained as a hybrid of public and private space, offering a transport hub connecting private sector visions of zero-carbon cycle, ultralight rail, and river transport solutions, and a retrofitted metabolist urban framework for reprogrammable and adaptable urban spaces that are granted the ability to adjust, transform, or fade to avoid obsolescence by prescribing it. In a very real sense, London exists because of the bridge. Before what is known as the Claudian invasion of Britain in AD 43, there was no London. The legions of the Roman army advancing northwards found the Thames a barrier which needed to be crossed. Still utilized today, depicted on the column of Marcus Aurelius and the Titurius plates, pontoon bridges were described as an essential part of the Roman war machine. They served as a quick and temporary means of crossing and helped establish the ancient Roman settlement of Londinium. In AD 75, after successfully invading the Celtic settlements, the Romans constructed a permanent bridge. Similar to the Rhine Bridge depicted by Palladio in 1570, it can be speculated that a similar Roman timber-piled bridge was deployed at a settlement to establish a permanent avenue for trade. In 1209, following the destruction of a series of intermittent timber bridges, the newly appointed Bridge House Estates funded the construction of a new permanent stone bridge. Built at the entrance to the City of London, it included a series of dwellings, shops, and a chapel, a small community created by the Bridge House Estates to generate income for the maintenance of the crossing. The bridge became not only an entry into the city, but also a centre for community and trade. Old London Bridge grew under the stewardship of the Bridge House Estate, continually adapting its architecture over its 600-year tenure to suit the wavering zeitgeist related to its density, commerce, and vulnerability to fire. The bridge morphed as a product of its different eras, and a testament to its infrastructural and cultural significance to the City of London. However, in 1831, following the removal of all buildings from Old London Bridge, the 600-year-old structure was nearing its obsolescence. During the first Industrial Revolution, a shift to utilitarian practicality saw a new bid to design a bridge with pure traffic and crossing capacity. New London Bridge was built west of Old London Bridge, allowing its predecessor to operate during its construction. The foundations were laid within a timber cofferdam to ensure the correct placement of its piles. Temporary timber structures called centres supported the stone structure until the arch was completed. This study highlights an interesting sequence of construction performance that is generally erased and forgotten after completion. Designed by John Rennie in 1823, this iteration focused on the utilitarian vision of the transport-centric connections of Londonopolis. Bridges increasingly took on pure transport functions to accommodate an increase in traffic, where habitation and community became less of a priority for the city. Rennie's vision was short-lived, however. In 1962, cracks were discovered on the piers of New London Bridge, which was a result of the increased car-centric load of the Second Industrial Revolution. The bridge was once again obsolete. The London Bridge Act of 1967 approved the replacement of London Bridge and the sale of the existing granite-faced stone to American oil tycoon to be reassembled in Lake Havasu, Arizona, continuing its capitalist legacy as a tourist attraction. The act was approved on the condition that the replacement remain at the existing location, to retain its pre-existing abutments and connections to operative road infrastructures, and without interrupting the flow of road or river traffic. The seemingly impossible task devised a series of 4 phases and a large temporary gantry. The sequence began with the removal of the existing upstream quarter and the construction of the west span to partially divert traffic for the further demolition of the existing bridge. The downstream footpath of the old bridge was removed to enable the construction of the fourth span. Once completed, all traffic would be diverted to both perimeter quarters, leaving the existing bridge obsolete. The decommissioned bridge could then be demounted, utilizing the gantry to stabilize and lift the archstones out for shipping. Finally, the middle spans of the new bridge could be assembled. Connecting all quarters would mark its completion in 1973. Discovered at the end of each precise analysis of historic case studies was a shift to obsolescence, the death of a bridge and the birth of a new one. The underlying notion of time and obsolescence in the context of hard infrastructure typically remains obscure due to its inherent prolonged lifespans. But through the study of the iterations over a substantial but precise timeline, we find the impermanence of infrastructure through its multiple failures caused by natural and societal systems alike. Here, the site of London Bridge becomes an entryway into the new pedestrianised city, where the crossing not only serves as a physical connection between the south and the city, but also an ideological transition between 2 urban models. Its persistence as a crossing and continual interactions with the river has developed a rich historical footprint, embedding the physical provocations of bridge building deep within the strata of the river, frequently overlooking the impact on natural systems with a central focus on the benefit of human interests. In this new chapter of urban infrastructural organization, definition of a bridge becomes dated. An obsolescence of the current crossing in 2050 is speculated through the rise in our adaptive approach to reuse in architecture and the death of the personal motor car. It explores the next iteration of the crossing as a monument to the past and a hub connecting people and new visions of inhabitable infrastructures. Beginning an exploration into the possible variations of the next crossing, an emphasis on adaptation rather than radical change was discovered. Following the pedestrianisation of the City of London, the once neutral linear connection becomes polarised and updated to serve as a link between distinct urban typologies. The bridge once again becomes the gateway into a new established city. Inspired by schematic subway maps, I was interested in exploring complex arrangement of programs in schematic form. Similar to the Halley 5 station, this schematic for a mobile research apparatus investigates methods of adaptation to address obsolescence based on stimuli derived from historic and novel technologies. London Bridge represents artificial ground, suspended above the Thames vertically connecting river, land and air. In the second schematic, a discrete transportation conversion hub is proposed to diversify transport entering the city, utilising cofferdams at the existing fluvial footprint of London Bridge to connect tunnels to river to air. The final schematic takes a less provocative and destructive stance. It acknowledges the territory and personhood of the river, establishing the river entity. The rights of the river become a significant driver in the types of construction or interventions taking place on the Thames. A retrofit strategy is therefore appropriate to address the obsolescence of the existing bridge, whilst acknowledging its boundaries and provide a suitable testbed for the reimagining of our transport crossings. Inspired by the repertoire of metabolism in Rem Koolhaas's rehabilitative Project Japan, I took inspiration from the architectural interventions developed by the Japanese metabolic group, presented in the Osaka 70 Expo and more notably in the independent works of Kisho Kurokawa. The typological distinction discovered sets the foundations of my design approach to the metabolist framework. Inspired by the photography of Todd McKellen's Take Objects Apart, I began utilizing animation as a tool to explore the existing bridge. I classified the component categories and evaluated each family based on its value to the proposed conversion. This included structural, environmental, social, and non-human value. The arbitrary measure utilized attempts to prioritize components for different R strategies to ensure proper recommendation is specified for each existing component. Functioning structural elements removed from the initial retrofit are certified and donated to the fictional city building materials depository. This prevents a devaluation of assets and generates a catalogue of certified bridge building materials ready for specification, offsetting the construction waste culture and embodied carbon emissions related to extraction and manufacturing of virgin components. Initial retrofit design imagined a sequential deconstruction of the existing bridge, retaining structural elements such as the pier, abutments, and diaphragms to minimize impact on the river entity. The soft demolition phase removes the finished elements before separating the four girder spans. New structures inserted between the spans and connected to the existing diaphragms, allowing the removal of the existing tendons, decommissioning London Bridge. Maglev track is installed to allow a permanent gantry to occupy the span. The gantry system is used to convert existing girder cluster segments marked by interval diaphragms to habitable capsule unit zones. This initial process design is a linear progression, beginning at a deconstruction and ending at a habitable and adaptable artificial ground. Further iterations were developed alongside structural and environmental consultants. The initial composite design attempted to mimic the clearance pattern of the existing bridge. However, this arrangement goes against the conventional truss span depth ratios and weakens the truss effect. Iteration 2 subverts Port Authority laws on central bridge height clearance to prioritize the habitable aspects of the bridge. The intradose system takes structural elements under deck, allowing a clear extradose zone for habitation and reconfiguration. Additionally, the lightweight and slimline cable-stayed system is deepest at the centers, providing suitable framework cavities for capsules and other modular systems. Developed alongside an environmental consultant, Iteration 3 addresses the materiality of the framework, adopting high-performance steel components and coatings for bespoke structural connections and reclaiming universal steel components where appropriate for structural members. Attempts to offset high carbon emissions attributed to steel production by sourcing reclaimed alternatives or by improving the durability and lifespan of the framework. All nodo and deflector components are designed for ASTM 514 high-strength steel alloy with 1650 steel strands and twisted steel cables of various sizes. Overcompensation in cable strength, alongside tension hydraulic adjustment systems, extends the lifespan of the framework, allowing it to adapt to different future load cases achieved with minimal calibrations. Integrated services embedded within the structural frame provides essential resources for habitation. Pressurized provision of water and waste systems counteract the effects of gravity in a horizontal unicore system, and a centralized fresh air heating and extract system keeps the interior spaces at dew point, utilizing the suite of environmental sensors embedded in capsules. Von Mises stress and deflection simulations were run in a cloud-based analysis software to visualize the impact on calculated load cases. Results suggested a 60% overcompensation for the maximum load case, which is beneficial for the proposed growth and expansion. However, if not under consistent loading or serviceability limit state, structural deformation could take place as an excessive positive camber increases the risk of material failure. To address the question of achieving a consistent serviceability limit state, a permanent gantry system is incorporated into the design. Introduced in the early stages of the retrofit, the gantry is not only responsible for the initial conversion, but is also an apparatus for perpetual maintenance, recalibration, and adaptation. Portal frame overhead gantry allows the movement of cargo laterally, making it useful for the rearrangement of module systems. However, the overhead gantry lacks maximum height adjustment options, making it susceptible to obsolescence. The cantilevered gantry can be adjusted for height, whilst achieving its desired reach as the lower cantilevered section extends and upper section retracts to recalibrate its center of mass. However, this arrangement lacks the rotational or overhead transfer of cargo laterally. The luffing crane allows the gantry to operate at a fixed level and achieves different height requirements with the articulated arm. What it lacks in load capacity as compared to the previous iterations, the rotational and precise articulation of the crane serves as more utility to the adaptive system. To power the onboard maintenance and service systems, renewable energy is generated on the bridge, utilizing investments in private sector innovators to incentivize the development of clean energy to power transport and infrastructure. A fictional solar tracking PV system designed and operated by Panasonic incorporates a distributed tracking system, allowing individual panels to seek the sun with integrated sensors and align their surfaces to obtain maximum yield. Marine energy developer Open Hydro is commissioned to design and operate the marine mammal-friendly open center turbine generator, installed at the piers to generate and provide electrical energy for the inhabitants of the bridge. Surplus energy is partially stored on board or sold to the city for further investment returns that are frequently reinvested in new visions of inner-city zero-carbon mobility. The introduction of ultralight rail operated by Tesla and Transport UK features automated maglev platforms that seamlessly connects passengers to driverless pods running on the same track system as the gantry. The reintroduction of the river hub diversifies cross-city commutes by utilizing the Thames and its bridges as conduits to traverse long distances, with connections to electric cycle and ultralight rail systems as last-mile solutions to connect commuters to their final destinations. To address the building sector's issues of high material costs, energy consumption, and greenhouse gas emissions, the capsules are additively manufactured, utilizing 3D printing to achieve enclosure. Integrated into this perpetual supply chain of turning waste into building materials, bioplastic materials and insulation sourced for the capsules are made from renewable biomass sources. These materials are biodegradable and have a lower environmental impact compared to traditional petroleum-based plastics. Additionally, reclaimed steel is withdrawn from depositories when needed to captively assemble structural systems into capsules, embedding a prescribed obsolescence, prompting replacement when the closed system is no longer of value to the user. Inspired by Dune and Ravi's United Micro-Kingdoms, in hopes to envision and integrate ideas of governance, equality, trade, and technology into this rediscovered city typology, in the year of 2100, the fictional bridge is occupied by 4 politically polarized tribal entities. The new Metabolist Authority is tasked with the overseeing of maintenance, safety, and adaptation on board the bridge. They operate mainly within the gantry and deals with the movement of capsules, recalibration of weight systems, and the occasional firefighting. The Eco-Urbanites Collective fully embraced the decentering of the human and operates a two-sided system of governance, which deals with the natural and the artificial. They primarily operate and maintain energy systems, supplying power to adjacent tribes, whilst also providing flora and fauna strategies for the new bridge typology. The Zero Carbon Mobility Task Force depends heavily on the energy supplied by the Eco-Urbanites. The task force is organized entirely by market forces and uses the Bridge Foundation Fund to invest in private sector innovations to incentivize and promote sustainable electric transportation visions for the pedestrianized city. The Order of Autonomous abandons most forms of centralized regulations related to trade and commerce. The Concealed Order provides opportunities for individuals to operate free markets for unregulated trade based on the principles of voluntary exchange, private property rights, and minimal governmental intervention. The London Bridge Institution is founded on the basis of progress and adaptation, learning from its rich historic precedents of obsolescence, failure, and adaptation, and introducing new ideas of equality, occupation, transport, and energy. The new Metabolist iteration distresses the contemporary meridian of orthodox transport infrastructure and reclaims the bridge as an inhabited urban typology for the sharing of technology, ideas, and community.